Hi, this is Karl Neilson, and this is my oral presentation for assessment number 1. So let's just get right into it. So I started out with this. I just wanted to model some sort of cap that would limit the growth that the amount of gold players would have as it reached the total amount of players, that being 10,000. So as the amount of gold players reached 10,000, the growth would drop down to 0. So I start off with this, just 10,000 minus G. You can also think of this as the amount of silver players that there are. And in order to model the gold players growing, actually, I just took a G and multiplied it by that term. This made sense to me because it was like we have our gold players and we have our silver players, and we're multiplying them together to sort of balance them out in a way, so that it's never going to reach over 10,000, but it's also going to grow from the bottom up. And then I just took some arbitrary win rate of 0.25 or 25%, and multiplied that by G. So 25% of the time a silver player will beat a gold player and then get turned into a gold player. So that's what I did for that. Um, Now this was a good start for me. It was kind of confusing though, because as I was modeling this, I was getting some weird results. So I rearranged it in this way. Um, we can see that we have the 25% win rate, the gold players. We also have this other random constant of 10,000. That just didn't make sense to me. So I decided to just get rid of it. And so now we have 25% win rate, the amount of gold players total, and then we can think of this term right there as the percentage of silver players. So as the gold players reach 10,000, the percentage of silver players is going to go slowly down, and this is going to balance it out. We also have, if you look down here, our initial condition where at t equals 0 time, we're going to have 50 gold players. So then I did a slope field by hand for task 2. Just a quick one by hand, just to kind of show the proof of concept. I also did it in a computer just to make it look a lot better. So as we can see, if we look at any line going across, the slope is going to be the same at all those points. So the slope is, or the rate of change is independent of our time. It doesn't matter. Only the amount of gold players makes a difference in our rate of change. We can see that as, you know, the gold players are few, our rate of change is going to be slower, which makes sense because there's less gold players to convert silver players, if you think of it that way. So it's going to be small down there, and it's going to get steeper and steeper as we reach about 5,000 or halfway. It's going to be at the steepest point, and this makes sense because this is when practically not in reality, but you could think of like half of the gold players are going against half of the silver players. So there's the most mixing you can think of. But then as we reach the top, it starts to drop off as we reach, that 10,000, as we get fewer and fewer silver players. So now we get into solving it. So I tried rearranging it in this way to try and solve it. It might have been able to work. I couldn't think of a way to do it. You'd have to use the inverse product rule, I guess. I just couldn't think of an integrating factor that would make this work at all. So I abandoned that. And instead, I just took both our terms that had g in it, and I just divided each side by that to move it over from the one side onto the other side. And now this term in here, this whole term looks very confusing. We have fractions and fractions. I don't know how I would integrate this. It'd be very difficult. So we're gonna put that into a partial fraction decomposition in order to get it into some more simple terms that are easier to integrate. So we just have a and b as our different constants. We just multiply our two denominators to the other ones. This is just multiplying by 1 in reality, because each of these, this is 1, and then that g and that g are both going to be 1 together. So we get that. And as you notice, all our denominators are the same, so we can just multiply everything on both sides by the denominator to get rid of them, and we're left with this. A lot easier to look at, and this will be very easy to solve, especially once we take that a and distribute it into into those parentheses right there. So now we can imagine our g is a variable. It can be any value. So if we take that value to be 0, let's say, then these two terms, this one and this one, they're gonna be 0 if we take that g to be 0. So then we're left with just that, the 1 equals a. So we take 1 equals a, and we can set all the a's in our previous equation to 1. So we're left with this. We can take those two ones, just subtract them from each other, so we're left with 0 on that one side. And then we can rearrange this to that. And then we can just simply divide each side by g to get our value for b, which is going to be 1 over 10,000. So now we've gotten this more complex, harder to integrate thing and made it into these two terms. This one term on the right, on the far right, it looks kind of confusing, but I'll rearrange it and it'll make it a lot easier once I get to that. So this is our new differential equation rearranged with that partial fraction decomposition. This is going to make it a lot easier to integrate. And that's where I made that simpler. I just took that 10,000 from the numerator, multiplied it by the bottom in order to make that's a lot simpler. It was a lot easier for me to understand. So now we can just integrate by each side. We know the 1 over g and the 1 over 10,000 minus g, those are just going to be natural log functions, ln. And we're taking each side, we're taking the integral in respect to t, so dt. So then we're left with this, ln of g minus ln of 1000 minus g equals 0.25t plus c. I just took the c from the left side and moved it onto the right side, just combine them together just to make it easier to, we're just messing with one c at that point. So we take e to the power of both sides. This will still be true. And we can just rearrange this in a way where we take the one ln that we're subtracting from the other one, and we can move that below, and we take the c and put that just as a constant in front. So yeah, there's where we take the ln's, put one over the other, and then we can, knowing that e to the ln of something is just going to be that thing, we can simplify this to that right there. Now, this is kind of still hard to figure out what our g is going to be, so I'm going to flip it around. You can think of taking each side to the power of -1, or, just flipping them around, taking the reciprocal of each side. And we get that right there. And then we can take these two terms on the left, separate them out into those. We notice that g over g is just going to turn into 1. So we can add that onto the one side. And then we can just do some rearranging to get our g isolated. We're just going to put the whole term on the right, that was on the right in this one and just put it below the 10,000. So this is our general solution. And then we got to remember that our initial condition is going to be at time 0, it's going to be 50. So we can just plug in 0. We know e to the 0 is going to be 1. So then we're left with 10,000 over c plus 1 equals 50. We do some quick rearranging to get that. And from there, we can see that our c is going to be 199. So there we go. That is our particular solution for this problem. As you can see, we still have the 0.25, all the 1,000, 10,000. We have all the necessary parts to make this work. And if we take this and we graph it, as we can see, it matches very, very similarly. In fact, it's the same exact thing as the plots that we're getting from the slope field. And it does, over at this point over here, it does intersect at 50. So at time 0, it's 50. So our initial condition is satisfied from that. And as we can see, as we reach 10,000, it tapers off and starts to plateau, which makes sense. So yeah, that's how I solved this problem, and just some nice visuals to go alongside it. And thank you.